Okay, good morning, guys. Again, my apologies for being late, having some troubles connecting. But can you guys see my screen? Hindi ko siya pa rin nakikita sa monitor ko. But I hope on your end you can see my screen. I already started screen sharing. Kita nyo ba, guys?
Sir, sa akin po hindi.
Okay, let me just try resetting my screen share. Um, Okay, I think it should be on now. So, all right. So today we'll continue our discussion about Module 8, and it's about deriving the composite Newton-Cotes formulas. So the thing here is that gusto, di ba, nakita natin last time yung error involves sa interpolation as sa numerical quadrature rule, specifically sa Newton-Cotes. Tapos nakita natin ay minana niya lang yung error term mula sa interpolation theory, right? So the error now for the Newton-Cotes formula, which is the absolute difference between the actual integral and the integral of the interpolating polynomial, which we substituted for the actual integrand f, is actually equal to the same derivative factor that we have seen from the error in the interpolation, right? So it's the n+1 derivative of f evaluated at the number c all over n+1 factorial, all right? Times, instead of just omega of x, it will be the product, it would be the integral of omega of x over the interval AB. So halimbawa, sa trapezoidal rule, ito yung error natin. So trapezoidal rule, remember n+1 is the number of points that we are using, right? So sa trapezoidal rule, dalawa yung ginagamit nating points. So ibig sabihin ng error para sa trapezoidal rule will be the second derivative evaluated at the number c all over 2 factorial, all right, times the integral of x minus a times x minus b dx from a to b. Okay? So bakit ganun? Kasi ang omega, product siya ng mga x minus all of the abscissas. So in the trapezoidal rule, remember we're using two abscissas. We're using A and B as our interpolatory abscissas. So meron tayong omega equals x minus A times x minus B. We take the product, yun yung magiging error sa interpolation. Pero dahil ginamit natin yung interpolating polynomial to be the integrand, so yung error ngayon ay nasa loob, yung error na supposedly manggagaling mula dun sa factor omega will be replaced by the integral of omega. Sandali, mukhang nawala na naman yung screen share ko. Hold on, guys. Okay. So, ito yung error sa trapezoidal rule. And if you will be patient enough to evaluate this, I think you'll get f double prime of c all over 2 times b minus a cubed all over 6. Okay. Now, because you'll just need to multiply out x minus a and x minus b, you'll get a quadratic polynomial, then you integrate it, you plug in a and b, that's fine, okay? So that's how we calculate the error for the basic trapezoidal rule. And then we see here that it seems that as we increase the number of points used, halimbawa sa general Newton-Cotes, all right? Pag pinalaki natin ang pinalaki si n, mukhang paliit ng paliit yung error kasi yung n nandun siya sa denominator inside the factorial, and we said factorials grow very fast. Medyo kailangan lang natin maging careful kasi natutunan natin sa interpolation theory, okay? Na the more points you used, theoretically, the error should go down, pero whenever using equally spaced points, nagkakaroon tayo ng problema, yung Runge phenomenon. And the Runge phenomenon causes the L infinity error to blow up because of the crazy oscillations that happen near the edges of the interpolatory interval. So hindi laging guaranteed nagaganda yung approximation pag napakalaki ni n. Kasi even though there is a 1 over n plus 1 factorial which will drive the error down, baka naman masyadong malaki yung magiging integral ng omega. Kasi the more points you used, the higher the degree of omega is, posibleng napakalaki ng values ni omega sa mga values that are very near A or very near B, which will sort of counter yung factor na 1 over n plus 1 factorial dun sa labas nung dito sa ever term. So if we want to avoid the Runge phenomenon and its adverse effects on the error, ang isang strategy ay pwede nating kopyahin mula dun sa konsepto ng splines. Remember, what we did in splines is that we subdivided the interval into several pieces, and on each of those pieces, we constructed a low-degree polynomial, pasted them together by requiring that the resulting piecewise function be continuous at the boundary points. And in some cases, we can afford to impose differentiability o yung smoothness dun sa mga boundary points. So ganun din yung gagawin natin ngayon. Hati-hati natin yung integration interval into several sub-pieces, and then on each of those sub-pieces or sub-intervals, we will use a Newton code formula, a basic Newton code formula, para ma-avoid lang yung pag-i-involve sa napakalaking degree ng isang interpolating polynomial, and at the same time, this is taking advantage of the property of integral, yung additivity ng integral, right? Now, I will illustrate it using the trapezoidal and the Simpson's rule, but hopefully you can discern the pattern and be able to use this or to use similar arguments in order to come up with the composite, say, Boole's rule, composite midpoint formula, or composite four-point open Newton Cotes quadrature rule, okay? So let's go back here and let's see how it is done. Okay, if we recall, the integral of f of x dx using the trapezoidal rule can exactly be computed as this guy. Ito yung ginagamit natin sa trapezoidal rule, yung area ng mga trapezoid formed by f of a and f of b being the heights of the trapezoid respectively, times b minus a over 2. And we have just seen earlier, kulang pala ako dito ng minus sign, okay? Kakaroon pala dito ng negative sa harap, right? We have seen that the error term is comprised of b minus a cubed all over 12 times f double prime of c, where c is a value from a to b. Tapos ang idea sa composite trapezoidal, instead of a single trapezoid, ganito kasi ginawa natin, a, b, dalawang points lang yung ginamit natin. Halimbawa, ito yung function ko, it behaves crazily over the interval AB. Tapos sabi ko, i-approximate ko lang to using a trapezoid determined by f of A and f of B. So this would be my trapezoid. Tapos yung area na makukuha ko ay ito. Pero medyo pangit pala yung example ko kasi naging relative minima yung f of A at f of B. So napakalaki nung underestimate dun sa error. But sometimes it could be good, as what we have seen earlier, about 8.2% yung example natin before. Pero this is one of the worst cases in trapezoidal rule. Now, if I will use the composite trapezoidal rule, what I'll do is to introduce some more subdivision points in for the interval AB, and for the sake of brevity or simplicity of derivation, let's just assume that we are using equally spaced subintervals. So kung hahatiin ko itong si AB into n subintervals, each of the intervals to have uniform length should be of length b minus a all over n, right? So ito si x0, ito si xn, and then this would be x1, x2, x3, and so on. And the distance between two consecutive x's would be h, okay, which is b minus a all over n. And then what I'll do is, on each of the subintervals, I will apply the trapezoidal rule. So ito si f of a, kukunin ko si f of x1, okay? And then I will draw the trapezoid determined by these two function values. And then this would be my first subintegral, all right? So ito yung unang tingi or unang approximate or unang partial estimate natin para dun sa interval from A to B. And then we'll also draw the second trapezoid. This time it's determined by f of x1 and f of x2, right? Kunin natin yung area ng trapezoid na yan. That would be our second installment. And then for f of x3, kunin natin yung trapezoid. Okay. And so on. This is a very simple extension of the trapezoidal rule, and yet it has its elegance, all right? Kasi ngayon, sa bawat piraso, napakaliit ng order ng interpolating polynomial na kinukuha natin. In fact, here you can think of it as integrating the piecewise linear interpolant, because ang ginawa lang naman natin ay connect the dots, all right? Two consecutive dots, connect it by a straight line, and then evaluate the integral. Okay, so yun yung idea ng composite trapezoidal rule. Composite siya kasi yung isang malaking interval AB, hinati-hati natin into several components. Tapos sa bawat component, in-apply ko lang si trapezoidal rule. Now, you could have done this in any way you want. Kung may program na kayo, halimbawa, nung piecewise linear interpolant from before, ipa-integrate nyo lang kay MATLAB yung piecewise linear interpolant na yon, then you'll be good. That would be the result, say, of the composite trapezoidal rule. Kasi yun nga lang naman yung idea ng Newton Cotes. Nag-integrate ka ng interpolating polynomial. Yung mga dinerive nating formulas will just be for the sake of an implementation from scratch. But you could have taken advantage ng formula ng algebraic ng code nyo for the algebraic interpolating polynomial. Dadagdagan nyo lang siya ng isang linya, which will require or which will ask MATLAB to integrate the polynomial that was obtained. Okay? Sa MATLAB, madali kasi mag-integrate. INT lang yung syntax of, I think, the function and the bounds. So, function A, B. Parang ganito lang yung syntax kay MATLAB. Double check nyo lang sa documentation ni MATLAB in case nakamali ako ng pagkakaalala dun sa syntax. Alright? But let's see. What if you don't have your formula for the algebraic interpolating polynomial ready? So, paano natin magagawa yung trapezoidal rule? Or I mean, kung composite trapezoidal rule, ang kailangan nyo ay yung syntax nyo sa piecewise linear interpolant. Sa basic trapezoidal rule, kailangan nyo lang ay yung code yun ng AIP, pero ang interpolatory abscissas nyo, dalawa lang. Yung A f of A at saka B f of B. Okay? Now, in any composite rule, ito yung idea. So yung integral from A to B ni f of x ay kukompute natin as the sum of subintegrals. So hatiin ko lang si AB into intervals. So A, B, again, this will be x0, x1, x2, and so on. I'll first approximate the integral from x0 to x1, add it up to the approximate integral from x1 to x2, and so on. Ito yung sinasabi ng integral. Mag-integrate tayo sa bawat subinterval. Let's take the sum, all right? And that would be our the integral, right? So walang nabawas kasi nga ito yung tinatawag nating additive property ng integral. Okay, now for the trapezoidal rule, as I have illustrated earlier, ganito yung gagawin natin. Integrate natin ito. So may integral dito sa kanan. Papalitan natin siya by the implementation of the trapezoidal rule. Remember, the trapezoidal rule says b minus a all over 2. So that means this is half of the length of the integration interval times f of a plus f of b. Yun nga lang, sa unang pasada, dun sa pang j minus 1 na pasada ng integral, or yung pang j na pasada ng integral, yung integration interval natin ay xj minus 1 hanggang xj. So if we compute for the length of that subinterval, it's gonna be xj minus x sub j minus 1. And hence, that's how we got here. Tapos sabi ng formula, i-divide natin by 2. Alright? So kasi nabago na ngayon yung interval, hindi na a, b. X sub j minus 1 hanggang x sub j na lamang. But nevertheless, the first factor should be the length of the integration interval or integration subinterval divided by 2. And then yung second factor sa trapezoidal rule, function value sa lower limit plus function value sa upper limit. Okay? Kaya there's a typo here. Dapat function value sa lower limit plus function value sa lower limit. Okay? So ito ay yung application ng trapezoidal rule sa pang j na subinterval. Okay? And then to get the approximate for the entire original integration interval, I'll need to sum up all of these subintegrals. Kaya meron diyang summation. Okay? So again, this is just a bunch of applications of the trapezoidal rule on the subintervals. Okay? And then let's look at the error. So the error on each application of the trapezoidal rule is the length of the subinterval cubed all over 12 times f double prime of c sub j, where c sub j, okay, is a number on the jth subinterval. Okay? So yung error, inadapt din natin para dun sa specific subinterval. So yung number c, kung saan natin ine-evaluate yung second derivative para dun sa error, ay isang number dun sa subinterval na ginamit natin. So I hope everything is clear here. Okay? Tapos, si xj minus x sub j minus 1, this is just the length of the jth subinterval. And we mentioned again earlier that for simplicity of derivation, we are assuming equally spaced points. Pero in theory, hindi kailangan equally spaced points sa trapezoidal rule. Actually, ito na talaga yung trapezoidal rule or yung composite trapezoidal rule. Pero kung i-assume natin na equally spaced yung mga abscissas, alright, okay din naman kasi mas maganda yung itsura ng formula because x sub j minus x sub j minus 1 will be replaced by the uniform length h. And then you take the over 2 there. Tapos ngayon, itong h over 2 na supposedly andito, hindi na siya dependent sa j, so this factor can come up or come out of the summation. That's how I got this. Right? And then let's see the expansion of the remaining term. So ito ay magiging f of x sub j, no? So first term, kapag kasi j ay 1, yung summation ay nag-start sa 1. So this would be f of x sub 0 plus f of x sub 1 plus f of x sub 1. This is what will happen when j is equal to 2. When j is 2, this would be x sub 2 minus 1. So that's going to be x1 plus f of x2. Third term would be corresponding to j equals 3. So this would be f of x2 plus f of x3. And so on until f of x sub n minus 1 plus f of xn. Okay? But remember, delete ko na to. But remember, x sub 0 is just a. So the first term is f of a, and f of x sub n is just b. So pwede ko itong palitan ng b. And then we just try to simplify it and see that, okay, f of a, punta ka dyan, ayun si f of a. Si f of b, ayun, nandun siya sa pangatlo. However, for all intermediate function values used, doble silang lumalabas dun sa formula. Here I got f of x1 plus f of x1, so I'm gonna get twice of f of x1. F of x2 plus f of x2 will result to twice f of x2. I have an f of x3 here, and I know the pattern. I will have another f of x3 somewhere over here. So I'll have twice of f of x3 and so on. Yung f of xn, doble rin yan kasi may f of xn dun sa preceding term. Okay? So that's why all of the intermediate function values are again given an additional weight 2 kasi twice silang lumalabas dun sa formula. Okay? And this is actually our composite trapezoidal rule when equally spaced abscissas were used. Pero kung again, hindi equally spaced, then ito yung gagamitin nyo. Okay? Let me just copy this out for later. And then let's examine further the error term. A similar thing will happen to the error term. You have x of j minus x of j minus 1. That's the length of the jth subinterval. That can be replaced by h. So we'll have h cubed all over 12 times the summation of f double prime of c sub j. Now, it's a little bit difficult to deal with this error term on its own because here we need to find unknown value c sub j's for all of the subintervals and then sum up their function values under the second derivative. Okay, but we can apply some tools from analysis in order to further simplify this guy, even though we don't know what exactly the c sub j's are. Okay. Now the extreme value theorem, na dun sa mga students ko sa 101, kaka-prove lang namin, all right? But the extreme value theorem guarantees that if your function is defined on a compact set, or kung yung Math36 version yung ginagamit nyo, kung siya defined sa isang closed interval, then the function will, or the continuous function will get its absolute minimum and absolute maximum on the on the interval AB. Now, the assumption here is that f double prime is continuous and differentiable. Okay, smooth yung function f double prime. So, dahil continuous at smooth siya, okay, sa interval AB, dapat may number C1 na magbibigay ng absolute minimum niya at may number C2 na magbibigay ng absolute maximum niya. And these two guys, C1 and C2, are on the closed interval AB. Okay? So therefore, that means the function value of C1 under the second derivative is less than or equal to f double prime of c sub j, but that will be less than or equal to f double prime of c sub 2 kasi nga absolute max at absolute min itong dalawang values na to. And this is true for all c sub j in the interval AB. Or sabihin natin for all j. To siya para sa lahat ng j, starting from 1 until n. Okay? Now, kung ganun, lagyan ko sila ng summation sa harap. Pag pinagsama-sama ko yung mga mas maliliit na values, mas maliit pa rin yung sum dun sa sum ng mga mas malalaki sa kanya. So I summed up small numbers. It's going to be smaller than this guy, or the sum of these guys, all right? This guy is, or these guys are larger than each of these guys, then yung summation nila mas malaki pa rin. Hence, we get this, all right, by the summing up argument. And then f double prime of C1 is constant with respect to j. Constant to, so lalabas siya ng summation. So magkakaroon lang tayo ng f double prime of C1 times summation ng 1, I going from 1 to n. Meron kang n summoned. So itong summation na to can be simplified as n times f double prime of C1. Ganun din yung nasa kanan, nag-add lang ako ng n na f double prime of C2. So the sum would be n times f double prime of C2. And then we can divide both sides by n and get this. And then at this point, I will appeal now to the intermediate value theorem. Now we know that f double prime is continuous by assumption on the closed interval AB. And then, dahil continuous siya doon, tapos itong number na to, itong summation na to times 1 over n, ay nasa pagitan ni f double prime C1 at ni f double prime of C2. Sabi ng intermediate value theorem, pag meron kang number na nasa pagitan ng dalawang function values sa isang closed interval, merong isang element ng domain o ng interval whose function value is equal to this guy. All right? Yun yung sinasabi ng intermediate value theorem. In other words, it is telling us that there exists a number C on the interval AB such that f double prime of C, yung function value niya, ay equal dun sa na-sandwich na number kanina. Yung 1 over n times sum ng f double prime of C sa J. And with this in mind, the original error term can be written as negative b minus a cube over 12n cube. In-expand ko lang yung h cube kasi yung h cube natin ay b minus a all over n. So ito yung nangyari sa kanya, b minus a over n cubed. May 12 na multiplier sa labas. And then this guy again, we said it can be written as how? Ito pala yun, okay? I multiply n both sides to get n f double prime of C equals the summation of f double prime of C sub j's, all right? So the sum of the C sub j's here can be written as n times f double prime of C. And then the n's will cancel each other out, leaving us with an n squared. Tapos yung n squared na yon, pwede kong isama dun sa isang b minus a mula, sa dalawang b minus a mula sa taas, isulat siya as h squared na lamang. Okay? Tapos may matitira kang b minus a dito. So essentially, the error term for the composite trapezoidal rule is given by this guy. Okay? b minus a times h squared all over 12 times f double prime of C. Okay? So mas maganda ngayon tingnan yung error term. And that will give us an idea of how the error in the trapezoidal rule depends on the value of h. Now we see that the error is a big O of h squared. Okay? Ibig sabihin yung error, again, ay nagpupunta sa zero kasing bilis kung paano nagzi-zero si h squared. Okay? Kasi doon lumabas yung h squared doon sa trapezoidal rule. Before okay, hindi ko na lang babanggitin yung technical detail na yan. But do you guys have some questions? I hope the derivation is clear. Okay? So if you don't have any questions, maybe I'll proceed to the example here in 8.2. And it implements the composite trapezoidal rule to evaluate this integral. The integral from 0 to pi over 4 of e to the x sine x dx, avoiding integration by parts. Who would like to perform integration by parts anyway, right? So, but if you will be patient enough to do so, you'll see that the exact value of the integral is 1/2. Now, let's try to see how the composite Newton-Cotes formula, rather more specifically, the composite trapezoidal rule will perform in evaluating this integral. If we will use 2 points, so 2 points yung gagamitan natin, so ibig sabihin from 0 to pi over 4, dalawa lang yung points na gagamitin ko, so therefore they should be 0 and pi over 4. And that is the basic trapezoidal rule, right? Ang step size natin ay pi over 4 kasi haba yun ng interval, alright? And then kunin mo yung function value sa 0, function value sa pi over 4, use the trapezoidal rule, you'll get a 0.10, which is not a very good approximation because again, we know the exact value is 1/2. So meron siyang error na 21.8%. So it shows that hindi ganon kagandahan kung basic na trapezoidal rule lang yung gagamitan ko. Now, this tells us, okay, we need to use more points in the numerical integration scheme. However, I want to be a little bit careful because e to the x times sine x is is an oscillatory polynomial, all right? Posible siyang mag-oscillate kasi meron siyang factor na sin x. So I don't want to be a victim of Runge phenomenon. So ayokong palakihin basta-basta yung number of points na ginagamit para makabuo ng isang malaking degree na interpolating polynomial na pampalit sa e to the x sin x dx. Because it might be susceptible to the Runge phenomenon. So what I'll do instead is to apply the trapezoidal rule or the composite trapezoidal rule, this time using 3 points, okay? So magdadagdag pa ako dito ng isa, which is the midpoint between 0 and pi over 4. So that's gonna be pi over 8. So tatlong points yung gagamitin ko. That resulted into 2 subintervals, all right? And each of these 2 subintervals would be of length pi over 8, or 0.39, or about 0.39, okay? So the x's that we are using are 0, pi over 8, and pi over 4. Compute their respective function values, and then use this in this formula. Oops, sorry. Remember, ito yung okay. Ito yung composite trapezoidal rule na na-derive natin kanina. So plug in f of 0 here. Oops. So it's gonna be f of 0 plus twice f of pi over 8 plus pi over 4 times pi over 8 over 2. So magiging pi over 16. Perform the calculation and we see that we are now nearer to the actual value kasi ang estimate na nating makukuha ay 0.52. Okay? Now that will have around just 5% error. And let's see if it really makes true on the promise na order h squared, yung trapezoidal rule. So let's compare what happened when we have the 2 points to what we have right now. So tingnan niyo yung step size. Yung step size ay nangalahati. So basically, the step size here was shrink by a factor of 1/2. So dinivide natin by 2 yung h ngayon. Dahil yung trapezoidal rule o yung composite trapezoidal rule daw ay order bigaw ni h squared. So pag dinivide ko si h by 2, dapat yung error madidivide by 4. Alright? Kasi magiging ano siya, h over 2 quantity squared, h squared over 4. So ibig sabihin, madidivide by a factor of 4 yung error. And true enough, from 0.10 na absolute error, okay, madidivide siya by something around 4, you see that the absolute error now is down to 0.02, which is close to 0.10, 90, 30, 47 divided by 4. Okay? And so, true to its promise pa naman so far, yung trapezoidal rule. Okay? Now, if we move along and use 4 points, okay? 4 na points yung gagamitin natin. Yung h ay pi over, ano na? Pi over 4 divided by 4, pi over 16 na. Okay? Ito yung mga function values ng mga x's. Ito pala yung function value ng mga x's. Apply the composite trapezoidal rule. You'll get an estimate which is at around with error around 2.40%. Okay. Now again, this is still in agreement to the theoretical convergence kasi ano nakita natin dito? So yung step size ngayon ay sort of parang na-divide by 3 kasi from 0.78 naging 0.26. So inisip ko to around 0.75. Ito ay around 0.25. So 0.75 or something around 0.25. Pag dinivide ko sila, na-divide by 3. So dapat yung absolute error, madi-divide din sort of by 3. And true enough, na-divide ba siya by 3? Hindi pala madi-divide by 3 lang. So yung h na divide by around 3, So yung error ay dapat ma-divide by around 9. Kasi order h squared ito. Na-divide natin by 3 yung h. So yung error dapat ma-divide by 3 squared or around 9. And true enough, 0.10 divided by something around 9, that will give us something around 0.01. And then you can go on and apply this formula using 5, 6, and 7 points, you'll get better and better estimates. So far, yung composite trapezoidal rule, at least hanggang n equals 7 or n plus 1 equals 7, medyo nasatisfy niya yung promise niya ng order of convergence. Okay? Any questions, guys? Okay. Okay lang ba kung sagarin ko hanggang 9:30? Late naman ako nakapasok. So I'll finish this up hopefully. Let's look at the second example here, or the second derivation here. So the next thing is, let's derive the composite Simpson's rule. Okay? Ganun pa rin naman yung idea. Babalikan natin yung simple Simpson's rule. Ito lang siya. Isa to dun sa mga closed formulas na na-derive natin last time. And then ito yung error term niya. Again, yung error term niya ay, kasi sa Simpson's rule, gumamit na tayo ng ilang points. Gumamit tayo ng 4 na points. Tama nga ba? Yeah, I think so. Sa Simpson's rule, 4. So kaya meron ka diyang fourth derivative of psi all over 4 factorial. Okay? Times integral ng x minus a times x minus b, tapos times x minus a plus b all over 2 dx from a to b. Okay? Pag in-evaluate nyo itong integral na to, tapos minultiply nyo dito, ito yung makukuha nating error term. Okay? b minus a to the 5th all over 2,880 times the fourth derivative of c. C going from, C is a number from A to B. Okay? So, ang kaibahan dito sa derivation ng ng composite Simpson's rule sa composite trapezoidal, kailangan medyo maging maingat ako dun sa pagpili ng sub-intervals o pag-define ng mga sub-intervals. Kasi kung matatandaan nyo, ang basic application ni Simpson's rule, A, B, gagamitin niya to, A plus B over 2. So on its own, the composite Simpson's rule utilizes 2 subintervals to begin with. Okay? Meron kang subinterval from A to A plus B over 2 at another subinterval from A plus B over 2 hanggang kay B. Okay? Now, that tells us that on every application of the Simpson's rule, dapat meron ka laging dalawang subintervals. So kung paulit-ulit natin gagawin yung Simpson's rule, halimbawa, kung twice ko i-apply yung Simpson's rule, dapat meron akong 4 na subintervals. Kung 3 beses ko siyang gagamitin, dapat meron akong 6 na subintervals. So that means the number of subintervals to be used should always be even. Okay? So if a-factor in ko na dun sa pagde-derive natin ng composite rule, yung fact na sa bawat pasada ng Simpson's rule, dapat meron akong dalawang subintervals. So the total number of subintervals to be used must always be even. Okay? So ngayon, hahatiin ko siya into an even number of subintervals. So if I want to use n subintervals, then we must have 2m, or we can let it to be equal to 2m. Kasi nga dapat yung total number of subintervals ay even. So kung hatiin ko siya sa n subintervals, where n is equal to 2 times some integer m, so dapat yung step size o yung haba ng bawat subintervals ay b minus a all over 2m. Okay? And then again, I'm going to appeal to the additive property ng integral, all right? Kaya lang, kailangan nating maging careful uli ngayon. Kung makikita nyo, ang mga bounds ngayon ay pinili ko to be the even numbers. Okay? Or yung may mga even subscripts. Bakit? Kasi tingnan nyo, eto. Oops, wala pala akong drawing na babalikan. So, alam na natin na hatiin ko siya into an even number of subintervals. Starting from x0, I'll have x1, x2, x3, x4, hanggang makarating ako sa b. So ito si A, hanggang makarating ako kay B, which is x sub 2m. Alright? Yung unang pasada ng Simpson's rule ay mag-approximate sa integral from 0 to x over 2. Kasi nga, yung unang application ng trapezoidal rule, ng Simpson's rule, dapat meron kang dalawang subintervals. Kasi 3 points yung gagamitin natin sa kanya. Tapos, nag-evaluate tayo ng integral, so no overlaps are allowed. So ngayon, tapos na akong i-evaluate yung or i-approximate yung integral from x0 to x2. Mag-start naman ako kay x2 ngayon. Tapos, dapat dalawang subintervals yung dadaanan ko. Yung second iteration ng Simpson's rule ay mangyayari over x2 to x4. And then the next iteration will happen from x4 to x to the power x4 to x6, and then from x6 to x8, and so on. And looking at that pattern, lagi lang pala ako nag-i-integrate mula sa isang even subscript papunta dun sa susunod na even subscript. So that's how we got this. Walang overlap na nangyayari. So the sum of these subintervals will give us the value of the overall integral. And then again, the idea here is I will apply the Simpson's rule para sa bawat isang integral na to. Okay? Now again, Simpson's rule require us to get b minus a all over 3, the length of the interval being on which we are performing the Simpson's rule, divided by 3. Divided by 6. Tama ba? Yeah, divided by 6. So ito, x2j minus x sub 2j minus 2, gano daw ito kahaba? But we know that the distance between two consecutive x's ay h. So ito ay h long, ito ay h long. So yung unang interval, kung saan tayo nag-i-integrate, ay length 2h. So this guy will be replaced by 2h. And then merong over 6. So maka-cancel lang yung 2 at saka yung 6. We'll have h over 3. H over 3 is independent of j, so it can come out of the summation as simply h over 3. Tapos, gagamitin ko lang yung Simpson's rule. Okay? Now, tingnan natin, sulat natin yung mga first few terms dun sa summation ng Simpson's rule. Okay? So, ito, papaulit-ulitin natin j going from 1 to n. When j is equal to 1, we'll have f of x sub 0 plus 4 times f of x1 plus f of x2. When j is equal to 2, we'll have f of x sub 2 plus 4 times f of x3 plus f of x sub 4. And then when j is equal to 3, we'll have f of x3 plus 4 times f of x5 plus f of x6, and so on. Okay, and then let's sum this up. Si f of x sub 0, siya lang naman si f of a. At once lang siya nag-appear, right? Hindi na siya naulit ever. So meron kang f of a dun sa summation. Okay? Tapos meron kang 4 f of x1. Meron pa bang x1 na nangyari? Wala na, no? Kasi ito ay 0, 1, 2. Ito ay 2, 3, 4. Tapos ito ay 2, 3, 4. Mali pala itong pangatlo ko. Dapat ito ay 4. Tapos 4, 5, 6. Tapos 6, 7, 8, and so on. So hindi na mauulit si f of x1. So meron akong 4 times f of x1. And you will see that that would be the same fate sa lahat ng odd subscripts, right? So yung f of x1, f of x3, f of x5, f of x7, and so on, di na siya naulit. So lagi lang silang may 4 na multiplier sa harap. So, kinolekta ko lang lahat ng odd subscripts, isum ko sila, multiply ko by 4 yung sum. Now, dun naman sa mga even subscripts, except f of a and f of b. Kasi si f of b, siya lang yung nandito sa dulo. F of x, 2m siya. So, hindi siya mauulit. So, meron ka lang plus f of fb dun sa dulo. F of b dun sa dulo. Now, for all other intermediate x's with an even subscript, like f of x2, naulit siya dito, f of x2. So that's why we get twice of f of x2. Tapos si f of x4, naulit siya dito sa pangatlong term. So I'll have twice of f of x4. Mangyayari to sa lahat ng even, maliban lang kay x0 at saka kay x2m. Kaya itong summation na to ranges only from 1 to m minus 1. Para dito, f of x2, f of x4, f of x6, hanggang f of x sub 2m minus 2. Okay? So this guy, is the composite Simpson's rule. Okay? And then the error term is just the summation of those error terms. So minus h to the fifth over 90 of the sum of the f double primes. Bakit siya naging h to the fifth 90? Because remember, we'll have this guy is 2h to the fifth all over 2880. So we'll have here 2 to the fifth, which is 32. It shares a common factor with 2880. So pag nilowest terms natin, magiging 1 over 90 lamang. So kaya naging h to the fifth over 90 lamang ito. And then again, we can appeal to the extreme value theorem and the intermediate value theorem, katulad ng ginawa sa Simpson's rule, para mapaganda yung itsura nung sum ng f double primes. And here we will see that will simplify to negative b minus a h to the fourth over 180 times the fourth derivative evaluated at the number c from a to b. Okay? And here that's evident that the composite Simpson's rule is of order big O of h to the fourth. Ibig sabihin, the error will diminish as fast as how h to the fourth approaches 0. Okay? Tapos kung titingnan natin yung example dito, makikita natin na napakalaki ng improvement mula dun sa trapezoidal rule. Kasi sa trapezoidal rule ay big O of h squared lang siya. Okay? Pero dito mabilis nagze-zero yung error. Kasi pag gumamit ako ng 3 points, basically this is your simple Simpson's rule. Yung yung relative error is less than 1% na kagad. Actually, it's a 0.00048. So napakaliit niya na talaga. It's almost just below a 20th of a percent. Okay? And then you see that the size of the absolute error here is 10 to the minus 4. Tama nga ba? 1, 2, 3, 4. Yeah, it's 2.4 times 10 to the negative 4. So the absolute error is of size 10 to the negative 4 using only 3 points. Pero kung babalikan natin yung trapezoidal rule, kailan yung error naging 10 to the minus 4? Actually, wala pa nga eh. Kasi yung error dun sa pinakamaganda, sa 7 points na ginamit ay 1, 2, 3. 3 times 10 to the negative 3 lamang. 7 points na yon ang composite trapezoidal. Pero sa composite Simpsons, order 10 to the negative 4 na kagad yung meron tayo. Okay? Tapos dagdagan mo pa. So 5 points yung gagamitin ko. Kung meron ako 5 points, meron akong 4 na subdivisions. 4 na subintervals which is even as what we have expected. Even dapat yung number of subintervals, so ibig sabihin odd dapat yung number of boundary points na gagamitin. Kasi yung unang interval natin from x0 to x1, pangalawang subinterval ay x1 to x2, pangatlo ay x2 to x3, then x3 to x4. Kaya sure ako even yung number of subintervals. Apply the composite Simpson's rule that will give us an approximate which is close to the very close to the actual value to the point na yung absolute error ay order 10 to the negative 5 na lamang. Okay? And let's see if that is true to what we expect. So yung step size dito ay 0.39. So that's around 0.4. So ganito yung parang rough convergence analysis. Ano kung makikita natin na at par ba with the theoretical expectation yung paggalaw ng ating error, ng paggalaw ng ating algorithm. So yung H dun sa 3 points, pagpalagay natin around 0.4. Yung H dun sa bago ay around 0.2. So it looks like na divide by 2 yung H. So kung si H ay na-divide by 2, yung method ay big O of H to the fourth, so dapat yung error ay madi-divide ng 2 to the fourth. And 2 to the fourth is around 16, right? Or actually, it's exactly 16. So dapat yung error, siguro, pagpalagay natin madi-divide by 10. And true enough, or actually kahit 20 nga eh. So, pagpalagay mo na 20, yung factor dapat na mababawas dun sa error. Yung error natin ay big O of 10 to the fourth, pag 3 points yung ginamit natin. Then kapag ka 5 points na yung ginamit natin, magiging 10 to the negative 5 na yung magnitude niya. So na-divide siya by 10. Yung coefficient dito ay 2.4, yung coefficient dito ay 1.6. Their quotient is around 2. So indeed, na-divide natin yung error by around a factor of 20. Ang in-expect natin ay around 16. And it seems that's the case, right? And then kung makikita pa natin dito, yes, paganda pa siya ng paganda habang dumarami yung points na ginagamit. Okay? So this is one thing about numerical integration formulas. Hindi ganon siya ka-affected ng step size. Hindi katulad ng numerical differentiation na napakalaki ng epekto ng step size sa machine implementation. Kasi kung matatandaan nyo, yung total error sa differentiation ay merong h, halimbawa meron kang h over something plus yung machine epsilon ay something over h. Kung matatandaan nyo yung limit na kinuha natin, so yung total error comprised of the theoretical error and the machine error ay nag-approach ng positive infinity kapag kasi h ay paliit na ng paliit. That makes numerical differentiation schemes very unstable. Pero sa pag-compute ng derivative, gusto natin yung dalawang consecutive x's ay malapit na malapit sa isa't isa. And yet, sa machine implementation, hindi sila pwedeng masyadong malapit sa isa't isa kasi the error will blow up. Now, the thing about numerical integration, hindi siya affected ng ganong scenario o ng ganong phenomenon. Kasi kung babasahin nyo yung dulo nung handout, so I'll just leave it as a reading assignment now because I'm already 6 minutes late. Dismissal na, okay? So pag kinonsider nyo yung machine epsilon, alright? So imbes na si f of xj, yung nagagamit na data ni machine, ang nagagamit niya lang ay yung truncated version ni f of xj. Tawagin natin yung truncated version niya na f hat of xj. Kasi di ba, finite machines, ko-consider niya lang yung first few elements. Tapos meron ka naiiwan na truncation error na e sub j. Okay? So, ibig sabihin, pag in-apply mo si composite trapezoidal rule, ito lang yung mako-compute mo. Okay? Nakalimutan mong i-factor in yung contribution mula dun sa truncated values. Alright? Pag idinagdag mo siya, ganito yung magiging itsura. Okay? Yan, ito yung round-off error o yung total truncation error. Okay? Tapos ito yung theoretical error. Tapos tingnan natin ito. Anong mangyayari kapag ka-inassume natin na bawat e sub j ay may magnitude na bounded above by the machine epsilon? So ito magiging epsilon, ito magiging epsilon, ito magiging epsilon. Okay? So ito na yung total error. Okay? Ito pala yung magiging total error or bound para dun sa total error. Okay, then let's examine this guy. All right. So pag sinimplify natin yan, pinalitan natin yung mga e sub j's by the machine precision epsilon, which is an upper bound for the truncation error. Ganito lang yung mangyayari sa kanya. So yung round-off error ay equals to h over 2 times this guy times epsilon. Performing the math will give us nh epsilon. Pero yung nh, siya lang ay n times b minus a all over n. You can cancel the n's. So, ang matitira na lang na bound natin sa truncation error ay b minus a times epsilon. And the beauty about that is hindi siya dependent kay h. Nakadepende siya dun sa haba ng original interval times epsilon. So it seems that from this analysis alone, we can conclude na hindi magiging problema yung dami ng subintervals na ginamit. Kahit sobrang liit na ni h, hindi siya nakaka-apekto adversely doon sa total error. Kasi yung error due to the machine epsilon ay nakadepende sa haba ng interval na originally kinonsider natin times the machine precision epsilon. So we don't need to worry about the same fate na dinanas no numerical differentiation formula. Kasi kung matatandaan nyo, pwedeng ang itsura na ay h squared f double prime of c all over 2. Tapos meron tayong plus machine epsilon over h. Ito yung total error kay numerical differentiation. Ito yung due to truncation error or something like this. Okay? Pag kinuha mo yung limit nito as h approaches 0, magiging positive infinity. Pero pag kinuha natin yung h approaching 0 ng total error para sa numerical differentiation, equal lang siya sa b minus a epsilon kasi nga hindi na siya nagdedepende kay h. So nakadepende lang siya sa haba ng interval. So we can pick as little h as we want. Up to machine precision, pwede natin gamitin kasi nga hindi affected yung total error by the step size. Okay? So kaya usually, kapag ka meron kang choice, halimbawa meron kang differential equation, gusto mo siyang isolve numerically, you have two options. Use numerical differentiation or translate the problem into an integral equation, tapos mag-numerical integration ka. And usually, ang pinaprefer ng mga mathematicians ay integration, numerical integration. So tinatranslate natin yung differential equation into a weak form involving integrals kasi nga ina-avoid natin yung instability due to numerical differentiation na pwede nating danasin pag gumagamit tayo ng finite element methods. Okay? So if you have the option or if you have to choose whether to use numerical differentiation or numerical integration, especially in a machine implementation, lagi nating pinipili yung numerical integration. Okay? Now, I think that's it. I just have some clues for the lab exer 5. Sinabi ko to dun sa kabilang section. So, since it's already over time, kahit I made already up for my 10 minutes late today, you can watch the video, the end of the video for from section V. Nagbigay ako ng konting clues sa laboratory exercise 5.1. So if you guys want to have some idea how to do it and some hints, you can visit that video. Okay, but I'll stop here. Do you guys have any questions? Okay, if there are none, thank you for sticking around and kahit 12 minutes overtime na tayo. Good luck on exercise 5.1. Enjoy your weekend, guys. Take some rest, and then let's see each other again on Wednesday. Bye, everyone.